and welcome back to Allen High School's discussion of solutions as we, rapidly move through this year. Now, we were talking about dissolving rules. What are the rules for things to dissolve? And when we look at covalent molecules, we had the phrase like dissolves like. It's not quite as simple for ionic. We do start with the fact that ionics must have a polar solvent. And again, remember I said we're going to focus primarily on aqueous solutions in the very near future. Ionic, they do need a polar solvent, but that doesn't mean that they will all dissolve. What has to happen is this. I have an ionic compound, and in order for this to dissolve, I have to break that ionic bond, which is why some people argue that this is something of a chemical change. We're still going to call it a physical. And then I have to form water bonds all around the ions. Not only that, you're really breaking intermolecular forces between the water. So you have to break the bond, the ionic bond between the silver and the chloride. You have to break attractions between waters so that those waters are free to react with the ion. And depending on the balance of energy required to break, so it's energy required to break compared to the energy released when they form. Okay, when attractions form, energy is released. That will depend on whether or not it's going to be soluble. These are our solubility rules. All group 1 salts are soluble, and there are no exceptions. These are all going to be aqueous without exception. Okay? All nitrates are soluble without exception. All perchlorates are soluble without exception. All chlorides, bromides, and iodides are soluble, would be aqueous, except silver, lead 2, and mercury 1. Those would be solids. They would form a precipitate. We'll see that word again in a minute. I'm going to go ahead and include it here. Okay, now when we get down to the insoluble compounds, all salts of hydroxides are insoluble unless it's group 1, barium, strontium, calcium, and ammonium hydroxide. All right, all of them but the ammonium hydroxide, these are all considered your strong bases. I'm trying to find room to write that. There we go. Our strong bases and ammonia, some of our weak bases, are soluble. All other monatomic and polyatomic anions, except group 1 and ammonium, are going to be insoluble. Now, they've changed this chart a little bit because that's not quite true. When we look at the sulfate up here, we have a sulfate rule here. So this is going to be all other monatomic and polyatomics that aren't mentioned above is really what that's after. So when you've got your phosphates and your carbonates and things like that. So all phosphates are soluble except for group 1 and ammonium. All carbonates are insoluble except group 1 and ammonium. So here, insoluble means they'd be solids. The exceptions in this case would be aqueous. Okay, so that's our solubility chart, and you do need to know how to read that solubility chart. You do not need to memorize it until you have that opportunity to take AP chemistry with me. All right, we want to briefly mention water. We're going to focus in on water for the bulk of this time. Water is called the universal solvent, and it's because so much dissolves in water. It seems to be universal. It seems to dissolve pretty much everything. Okay, so we call it the universal solvent. And these wonderful properties of water really truly allow life to exist as we know it. And on your last page of your notes, we have some more insight into water. All right, let's take a look at these and make sure we can use your solubility rules to determine if it is soluble in water or other polar solvents. So sodium chloride, Rule 1 says all group 1s are soluble without exception. So that's aqueous. The rule on bromides, if you look at it, it is the 4th rule down, said all bromides are soluble except silver and lead 2 and mercury 1. All ammoniums are soluble without exception. All nitrates are soluble without exception. Fluorides are soluble except a handful, and calcium falls under that handful. Now, oxides, we're technically going to call this insoluble, but really we have to hedge our bets a little bit on that because oxides actually chemically react in water, and that's something you won't see till AP. So for now, we're going to pretend that oxides are just going to be insoluble, period. Calcium hydroxide is one of the exceptions to the hydroxide. It's what we call a strong base, and it is soluble or aqueous. Now, there's no rule for magnesium. There's no rule for carbonate. So carbonate follows under that last rule that says all other monatomic and polyatomic anions are insoluble except group 1 and ammonium, while magnesium is group 2. And so indeed that would be a solid. Calcium sulfate, there's not a rule for calcium, but there is a rule for sulfate. So you look for the rule for the cation, and if you don't find it, then you look to the rule for the anion. And there is a rule that says that all sulfates are soluble except silver, lead 2, mercury 1, and calcium, strontium, barium. So that would be considered a solid. Now, as a reminder, when you have an insoluble solid, so this is a picture here, this is forming, this is something like potassium iodide being dumped into lead nitrate. Well, when you put those two together, you end up forming lead iodide, and lead iodide is a solid. And when a solid forms, when two aqueous solutions are added together at the bottom of a solution, we call it a precipitate. And I actually found this mug online. There's a comic in your notes. I found this mug online. If you're not part of the solution, then you must be part of the precipitate. Okay. So if we wanted to summarize our rules, we have our covalent plus covalent. We follow the rule of like dissolves like. If it's covalent or an ionic, we have to look at the nature of the solvent itself. Ionic is not soluble in a nonpolar solvent, so this would be the solvent. It is soluble, but it is soluble in a polar solvent according to your solubility rules. And it really comes down to energetics. We're just going to give you those solubility rules and teach you to read those solubility rules. All right, let's forge ahead here. So let's look into the dissociation of soluble substances in water. We're really now zeroing in on aqueous solutions. So dissociation is the process by which an ionic substance breaks apart into its ions when dissolved in a polar solvent. Now, our acids will do this to varying extents, bases will do this, and ionic according to your solubility rules. So you got to follow solubility rules for your ionic. Now, if we have polar covalent, they may be soluble. They may be soluble because there is a force of attraction to the solvent, but they will not dissociate. we do not break covalent bonds. We do break ionic bonds and dissociate. We do not break covalent bonds when we dissolve. Okay? Now, for acids and bases, we have two types. We have strong acids. Acids are substances that have an H+ to donate. So here's our list of our strong acids. Strong acids dissociate 100%. And we're going to use a single arrow, a unidirectional arrow for our strong acids and bases. Weak acids and bases only partially ionize. So we're going to use a double arrow because they ionize less than 100%. That's some of the terminology that we're going to use here. So as we look at this, if we have a strong acid, it goes 100% to H+ as its cation. That's what defines it as an acid, and Cl- as its anion. Now I'm going to vary this slightly from your notes because technically it's only the first H+ that is strong on sulfuric acid, and I want you to learn it the correct way to prepare you for AP chemistry. So the first H+ comes off and it goes 100% to these products as written. NaOH is a strong strong base, and it breaks into sodium ion and hydroxide ion. Now, HF, to give you an example, ionizes less than 100%. It is a weak acid. We'll deal with those in the very last unit. And it's written, you notice it still shows the H+ as the cation and the F- as our anion. But the difference is we use the double arrow to indicate that it is reversible. It can go forward and reverse. And in fact, there's a lot more HF together than there are ions apart in this case. Okay, let's look at example 12.5. We have nitric acid, HNO3. That's a strong acid, you know, because you have to memorize that list on the other page. You have to know your strong acids and bases. It goes 100%. The H+ will come off. We do not take apart our polyatomics. So warning, warning, warning. Keep your polyatomics intact. Okay. Then we have strontium is +2, hydroxide is -1. So this would be strontium hydroxide. It's going to go 100% to strontium ion plus 2 hydroxides. Again, keep your polyatomics intact. We are not breaking covalent bonds. Now, do you notice when I took these apart here, that 2 went in the front, and that's because I had one strontium with the 2 hydroxides. Whoops, I can't draw that very well, OH. And we took them apart. So now, instead of the hydroxides being a formula writing issue, it's a balancing. We're counting because now the strontium ion and the hydroxides are completely separated from one another. So I'm counting 1, 2 hydroxides, so the 2 comes to the front where it's a count, whereas here it was that 2 is an issue of a bonding. Well, they're no longer bonded, so it becomes a count. And so that's how we write our dissociation reactions. And you're going to get some more practice in class. So until then, this is signing off.